Okay, so ladies and gentlemen, we're going to get going. Today's discussion, we're going to be covering a topic of great significance for two of the three approaches that we've covered for dynamic modeling within this class, to wit, agent-based modeling and discrete event modeling. Both of these approaches share in common a, um, uh, a feature of note, which is the occurrence of stochastics. And within the context of these models, stochastic effects can very significantly alter the results of a given model run. In today's lecture, we're going to be examining the impact that stochastic have on a particular model, and we'll be proceeding to examine some of the tools that many modeling packages provide, including AnyLogic, to help reason robustly about model behavior in the context of these stochastics. In other words, to reason about the model functioning, even though a given run of the model may have stochastic outcomes. We want to be sure that our conclusions drawn with that model are robust given these stochastics. They're not merely flukes. They're not merely happenstance. They're rather what we're seeing is something that's a regularity associated with the model and its assumptions, rather than a simple roll of the dice. So within today's class, I'm going to lead you through an exercise, a hands-on exercise, where we're going to be examining a model which has notable stochastic components. And we're going to be using that model to examine just how there are certain regularities that transcend the stochastics, as well as variability around those regularities that are associated with those stochastics. Secondly, I'm going to use this exercise to reinforce our understanding and our memory of how we undertake certain common-task and agent-based modeling, with an eye towards the final exam, where you may be asked to exercise some of these skills. So to that end, I'm going to ask you all to call up AnyLogic at this point, and we're going to undertake in quick time, and sort of on a double rate march, the creation of a model which is going to exhibit these sort of stochastic features. This model will be a nonlinear model. It'll be a model exhibiting nonlinearity, and specifically positive feedbacks. Why is it that I would choose that to exhibit a model such as that, to exhibit the occurrence and impact of stochastics? Does anyone have a sense? Why is it that we'd be interested in not merely in a linear model, a model where the whole is the sum of the parts in some sense, but rather a nonlinear model, and specifically a nonlinear model with positive feedbacks? What is it about positive feedbacks that makes them of particular interest? Yeah. Oh. That's exactly it. So in the context of positive feedbacks, in the context of systems where you have this reinforcing feedback, a small difference at one point in time can lead to a huge difference at a later time. Within these systems, we see the occurrence, in some cases, of what's known as chaotic behavior. Behavior that almost looks random, but actually is deterministic, and yet where if you start with 2 points that are very close together in state space, two states of the model that are very similar, just by the natural evolution of the model, even without stochastics, you get divergence in outcomes. But in today's class, we're going to be looking actually at the occurrence of stochastics and how that impacts these sort of nonlinear models. Okay? And it's for precisely the reasons that Paul articulated. Positive feedbacks, the occurrence of reinforcing feedback, amplifies the differences that would be exercised by stochastics in a linear model, and amplifies it to larger outcomes. So I've asked you to all call up AnyLogic, and I'll do the same here. And we're going to be getting going. So the model that I'll be looking at is a nonlinear model exhibiting positive feedback. That's similar to many such models we've built in the class. Where in the class, this is almost the beginning of a review session, and rightly so, because the end of the class, and nay, the final exam is nigh. Where in the class have we repeatedly seen the occurrence of positive feedbacks? What sort of models that we exhibited are both nonlinear on the one hand and have some components of positive feedback? First order delays, I welcome that suggestion. Unfortunately, they don't qualify under the characteristics of nonlinearity. First order delays are linear. Again, I welcome all suggestions of that sort, and certainly we spent quite a while talking about first order delays. But in a first order delay, the dynamics involved, the flow out of the stock is proportional to the stock. It's a constant times the value of a stock. And therefore, the rate of change of the system is linearly dependent on the current state of the system. But where did we see something? So those are actually linear. Moreover, they don't have a positive feedback. They have a negative feedback. They have a negative feedback because the larger the value of the stock, the faster the rate of outflow, and therefore it'll push back against the size of the stock value. If we increase the stock, it'll lead to more outflow, which will push back against that original change. If we decrease the stock from its equilibrium value, the flow will go down. There'll be a better balance between inflow and outflow, and the stock will tend to rise. So good suggestion, good idea, but in this case, that's not the type of model that exhibits these sort of both nonlinearity and positive feedback. What's the sort of model that would? Anyone? Okay, agent-based, but not all agent-based models exhibit both positive feedback and nonlinearity. We saw a very particular type that we went to again and again and again. Infection, in the context of infection. Why is there positive feedback in the context of infection? At an intuitive level, I mean, why do I say there's a reinforcing feedback? Good, precisely. So the more people that are infected, it leads to more people getting newly infected, which leads to even more people being infected. So there's this vicious cycle there. And it leads to instability in system behavior. One person being infected becomes 2, becomes 4, becomes 8 in short order. This is an example of reinforcing feedback. They're nonlinear because for someone to be infected, there's got to be both susceptibles on the one hand and infectives on the other. It's got to be these two elements of state that jointly influence it and influence a way that both are needed. So, ladies and gentlemen, today we're going to be building a model that is nonlinear and that is that exhibits this sort of behavior associated with reinforcing feedback, and moreover, it is stochastic, and hence an agent-based model will do well. So we're going to build here a new model, and this is going to be called SIRS and stochastics. Okay, stochastics. Model time units will be days, ladies and gentlemen. Days. Okay. Now, this model is one that's going to exercise a lot of things we've done many times before. In part because you may be asked to do them a few more times. from now. So I'm going to ask you to follow along, but we're going to proceed quickly because we are trotting well-explored ground for us. Okay, so I'm going to go add in an agent, call it person. Without much further ado, I'm going to lend that person a appearance. So I go and I'm going to place an oval in the origin for that person, meaning it will appear visually at the same point they are located logically. I'm going to characterize the position and size of this as being a size of 10. Okay. And I think I'll make that a little bit smaller, of 7. Okay. I do that by position and size associated with the oval. Okay. I am now going to go into main, and having placed that person in the population, I'm going to go create a population by dragging person into the population, into main, dragging the class person into main. It creates an embedded object, as it's called. It's going to be called population, and we are going to declare it to be a population of agents, where the number of agents will be given as 250. Okay. Okay. Next, we are going to drag in a parameter called population size. We drag it into main. This is going to be what sort of parameter? What's the type of it going to be? If it's a size of a population of quantized agents, it's going to be a what? An int, good. And it's going to be 250 by default. And we will make this population, in fact, depend on population size. Because we are all working on fast pace here, we're going to just leave out the this dot, and I'll just say population size. Next, ladies and gentlemen, we are going to go and go to an area where we can define a certain network structure for this population, okay? And I'm going to say we're going to be going to main. And if we scroll down main, this is what includes this population. If we scroll down main, we will find in the space and network, we can specify a network type. We're going to say, excuse me, that it's a distance-based network of connection range, ladies and gentlemen, 250. Okay? 250. Excuse me, I take that back. We're going to do it, I'm slightly adapting this example, size 50, okay? For this initial run, okay? So we're going to go place, we don't see any network. Why not? What are we still lacking here? Anyone tell me? We're lacking a layout. So we're going to need to do a random layout. We're going to spread them out in space. Alternatively, we could have gone to the population and frobbed the area where we specified their initial location. Instead, we're going to do it this time just through this layout. We're going to say random. So we're going to go run it. And what we should see is these people scatter around, but we don't see a network. Why not? What do we still have to do? Anyone? Yeah, we have to draw the connection. So we have to go to person. We have to scroll up and to go to connections here and go down to animation, and you need to select draw line connecting agent in animation. This is rehearsing some things we've done before, but I'm trying to do it in a compressed way. So you could watch this video perhaps a week and 2 days hence, and you could get a lot of the basics of building these models up, the mechanics of it. So you could focus on the more conceptual factors. Okay, so now we have a nice little network. This network is connected. Two individuals are connected if and only if they lie within 250 units of distance of each other. And because of the luck of the draw, because of the randomness involved in the placement, we see some individuals formed into clusters, other individuals more isolated or having just one or two connections. Ladies and gentlemen, here we have a model that exhibits randomness, structure of the network, the location of the individuals, but it doesn't exhibit stochastics. What's the difference between stochastics and just randomness? What is stochastics? Stochastics is randomness over time, It's random variables over time. It's associated with a process. So let's go add some change over time here. This is a totally static model. Okay, so in the next phase, what I'm going to do is to go and build up some dynamics associated with these agents, which is going to be reflective of their change in an infection status, okay? And we're going to use this to emphasize something you may not have seen before, but which is a useful pattern that you may wish to use at other times. So the first thing we're going to do is to go and draw in a state chart. State charts, ladies and gentlemen, describe at a single time, on the one hand, the possible states an agent can be in with respect to a specific concern. So we might have different state charts for different concerns. A given state chart could be for a particular concern, maybe for employment status, maybe for infection status, maybe for marital status. And that state chart for a given concern characterizes the possible states you can be in, the actions that change those states, typically moving between states, and finally, the rules that govern those actions. In fact, to be subject to infection, you have to be susceptible. But more than that, you have to receive a message, for example. Okay, so here we are. We're going to have infection state chart. There we go. And we are going to drag in 3 states. To wit, susceptible, infective, and, ladies and gentlemen, you guessed it, recovered. Okay. Now, we are going to further characterize transitions between those, the actions that can change state. So there's going to be a transition from susceptible to infective. What sort of transition do you think this would be? If this represents infection, what sort of transition would it be? Yes, it's a message transition. It depends on something outside happening, someone coming into contact with me that's infected. It's not merely occurring independent of other agents at a certain rate, right, or with a certain timeout. It's contingent on being infected by another agent. Next, there's a transition from infective to recovered, ladies and gentlemen, which is going to be associated with a rate transition. Okay, and we'll come back and set what the rate is in just a minute. Drawing again on review from earlier. And finally, there's going to be a transition back from recovered to susceptible, reflecting the fact that for this condition, like for many STIs, for example, immunity is short-lived. Even for things like flu, because of mutation of flu, immunity is short-lived. And this too, this one is going to be associated with a timeout transition. Okay, we're going to make this characterized by a timeout. Okay, now, in order to characterize the dynamics here, we're going to set a mean recovery time and a mean duration of infection. Because these don't vary on a per person basis, I'm going to put these in main. If we put them in each person, we'd have to specify them whenever we specify a population of people for each and every person what their values will be. Because it's shared, I'm going to put them up in main. So I'm going to go to main. I'm going to go down main, and I'm going to drag in, ladies and gentlemen, parameters. parameter here would be mean recovery time. Okay. And that is going to be, by default, 10 days. Okay. 10 days, ladies and gentlemen. Next, I'm going to specify a mean duration of immunity, and that is going to be but 30 days, much as might be the case for something like chlamydia and potentially gonorrhea as well, STIs of note. So, mean recovery time, mean duration of infection, of immunity, excuse me. These are both located in main. So now, if we considered the transition from infective to recovery, how would that relate so that we'll call this recovery? How would that relate to the parameters I just created? Can anyone say? Yeah, it's 1 over it. Why? Because the hazard rate, the chance per unit time of leaving a state, is 1 over the mean time in that state, if it's the only outflow there, or the only out transition there. So for recovery here, we have a rate per day of 1 divided by main dot, that refers to something in main, dot mean recovery time. Okay. Remember that that's true both for stocks, ladies and gentlemen, with outflows. If you have a certain hazard rate, a chance per unit time of leaving that stock, that hazard rate is, if that's the only outflow, it's 1 divided by the average time you spend in that stock. It's true for a state as well. With a transition, the hazard rate, the chance per unit time of leaving that stock, is 1 divided by the mean time in that stock. In both cases, it's because it's a memoryless process. No matter how long you've spent there, your chance per unit time, your chance, say, per day here, of leaving is the same. It's independent of how long you've been in that state. By contrast, ladies and gentlemen, this flow back from recovered to susceptible is quite the opposite. Your chance of leaving depends it's not that it's independent of how long you spend there. It depends totally on how long you spend there. It's a timeout transition. You leave at exactly a certain amount of time. I'm going to call this waning of immunity. And here we will show the name. And ladies and gentlemen, the timeout associated with this will be given by main dot, and it's going to be mean duration of immunity. Ladies and gentlemen, why is it it's not 1 divided by this? There, it's a time. It wants a time. By contrast, a rate is of unit 1 divided by time. It's probability per unit time. Probability is a dimensionless thing. It's number of coin flips that turn out positive over total number of coin flips. It doesn't matter if we count coin flips in ones and thousands and tens of thousands and millions. In denominator and numerator, it cancels. It's a quantity which is, as we say, dimensionless, a probability, and therefore a hazard rate, a probability per unit time, is of dimension 1 divided by time. So this dimensionless is of dimension 1. Okay, it's as we say, it's independent of dimension. Okay, so ladies and gentlemen, here, the waning of immunity here, it's looking for a time. A rate is looking for a hazard rate, which is of units 1 over time. This is looking, ladies and gentlemen, for a time. Okay, great. Okay, we are cooking with gas, ladies and gentlemen. I'm going to do 1 or 2 more things here that may open your eyes to some possibilities, because it's something we didn't exercise together. And if I ask you about it, I want to be confident that I've covered it decently in class. So let's go to main, and I drag in a custom distribution. And this is going to be called initial infection distribution. This is going to be oh gosh, what fraction of people are in different initial states with respect to their infection category, okay? Now, we want to characterize using this distribution. This is a custom distribution. We're going to say we're not going to be drawing from a normal distribution or multinomial or what have you, how many people are in each state. Rather, we'll draw it from a, as we say, empirical distribution. It'll be a histogram that will specify, that we'll sample from. It'll specify the probability of getting this outcome or that one, and we can set those numbers accordingly. So here, we're going to need to tell it which outcome to assume. So what I'm going to do here is we're going to add to our model something called an option list. This is an enum. We've seen it once before, I think, in class. So I just want to emphasize it another time. And this is going to be called initial state. This is an option list called initial state. Okay? Initial state is going to be one of a set of values, just like enums in Java can specify a set of categorical values, a set of discrete possibilities. The three possibilities here for the initial state are going to be what? What do you think they're going to be? Yeah, susceptible. And I'm going to call it susceptible state so we don't confuse it with the name of the state itself. Infective state and recovered state. Okay? So those are the possibilities we have in terms of our initial states in person. Were it only that any logic allowed you to specify a custom distribution over the names of states, but it doesn't. And it doesn't so easily. Okay, ladies and gentlemen, so this custom distribution, having defined this option list by adding it into our model like that, having defined that option list, ladies and gentlemen, we are going to go make this distribution be a distribution list over options, and which option list? Over initial state. And now we can specify what are the fractions of the population that should be of each of these categories. So we're going to set it, ladies and gentlemen, so that 80% of the individuals, 80% are susceptible. We'll set it so that 5% are infective and 15% are recovered initially. Okay? 85 to 15. Okay? There we go. So each of those is going to specify the proportion, and here the percentage, because they total up to 100, that are going to fall into different categories. Okay. Next, what we're going to do is we're going to associate a person with a category, okay? We're going to associate them with some initial state. So we're going to go to person, drag in a parameter, and this will be called initial state. This is all part of the same thought. This is what we call a software pattern, ladies and gentlemen. It's a set of elements that go together to deliver some coherent value. Here, the pattern includes an option list, it includes a custom distribution, and it includes a parameter whose type is going to be the type of the, anyone want to guess? Based on its name? It's initial state. Yeah, it's the type is the option list. Okay? We could say, I'll leave its default value blank there, but I will go back to person, and in the population, now we have to specify, because it's a parameter of person. Parameters' jobs in life are to state an assumption and to communicate that assumption from the point of creation to where they're used. Point of creation, ladies and gentlemen, for people in this model is associated with this population. So here we have to specify the initial state to use. And all we have to do here is we just have to call the initial infection distribution. We call it, and it's going to return something of type initial state. You may have seen that when I was selecting it. See, it returns an initial state. That's the initial state of that it's drawn randomly from this according to this distribution. 80% probability it'll be susceptible, 5% it'll be infective, and 15% it'll be recovered. Yes?
So if you had a custom create your initial population and then you were to add agents to it as your model,
you could do either one. You could tell it to draw from the same distribution, or you could specify, for example, this agent that's being born in the model has the same state as their mother, for example. So if the mother was infected, they're infected, or something like that. You can do either one, and I'd be glad to show how that could be accomplished. Okay, ladies and gentlemen, so we're going to go now put this into place. So that's a great question. And I will pause for more questions in just a minute, because I know I've gone kind of fast here. So finally, to implement this initial state, I'm going to go up here, and this is what I want. One of the things I want to show you. You can go down to the palette here in either agent or state chart palette, and we're going to create this branch, and from that branch will emanate links to each of the states. These links will basically allow us to go and come in. When we first come into the model, we could begin in either a recovered state, an infective state, or a susceptible state. And I'm no artist, but I will prefer if they're not hideously ugly, so I'm just going to just engage in frobbing behavior here so that we can have something that doesn't look absolutely horrible. Something along those lines. You'll notice that all three of them right now are red. Anyone know what that means? They're all the default. We're going to leave the default to be susceptible. Guess what the condition is going to be? So for this guy, for the one going to infective, there's a condition. Guess what the condition will be? If the initial state is equal to, if it's equal to, yeah, initial state dot infective state. You might actually be able to just skip that. In fact, you almost certainly can do something like this, because infective state should be known globally as being defined in this initial state, the state there. So it should be able to recognize that. And similarly, the one going to recovered, what would that be? What would the condition be for this guy? Same, but with recovered, yeah. Recovered state. Boom. Okay. So, ladies and gentlemen, what have we done? What hath we wrought? Well, we've put in place a pattern, and that pattern has allowed us a little bit of flexibility in the initial state of the model. So we put in place an option list with these names that designate each of the states in which a person can start. We put in place a custom distribution that allows for drawing in a random way which state we start in. It's a custom distribution over options. Then we associated each person with an initial state that's of the type of that option list. In other words, we have to specify one of these three states as their initial state. Next, we went up here in main and we set that parameter of the person to be created as drawing from this custom distribution. Finally, we set the person upon coming into the state chart to enter in a way that will route them to the appropriate state. So if they, by default, they go to susceptible, but if they're told their initial state is infective, they'll go to the infective state. And if they're told their initial state of recovered, they'll go here. Why is this useful? How did we accomplish this before? Does anyone remember, how did we put in place a mechanism to start some people infective at the start of the model? Yeah, we had an event, and the event did what? It Yeah, it sent messages using some sweet functional Java 8 code, I might add, whose beauty may somehow I don't get the sense that its beauty is absolutely seared into your mind. But if you look back on the video, the beauty is quite undeniable. But here, what we've done is we've divided a certain fraction of the population into each category. 5% start infective and are routed to this state. By contrast, we have 80% starting susceptible and fall by default into the susceptible state. And finally, the balance, the 15%, start recovered. They are delivered a initial state sort of parameter that's drawn from this that's recovered, and those ones go into the recovered state. And that initializes our model. Fair enough. Fair enough. Okay, so we're cooking with gas, ladies and gentlemen, here. But there's one or two things we still have to fill in for this model to be fully operational. What is missing from this? Transmission of infection is missing. So how are we going to put in place transmission of infection? Whither would that go? Where would that go? Where, how do I encode transmission of infection? The fact that one person can infect another here. Where does that have to go? Yeah, so we have to place it in infective, and there needs to be a transition here from infected to infected. In other words, periodically, whilst we're in that state, there's going to be a contact transition, okay? And this contact, and we will set it to be with a rate of 1 per day. And what's got to happen here? We have to send a message. How do we know we have to send a message? Well, because we have infection. For someone to be infected, they got to receive a message. So we got to undertake it with a message. This is quite different from system dynamics, where we just had a certain rate of going from susceptible to infected based on the fraction of people and other factors of people who are infective, as well as the transmittivity and the contact rate. Here, we're actually having a mechanistic description. I contact you and impart the infection. So, ladies and gentlemen, the action here will be send to random, not neighbor, but connected. Neighbor is for space. And I'll send the infection, the message. And actually, we are going to only have one type of message here. So it's just going to be it's going to be exposed, because they're, why do I say they're not necessarily infected? I just got rid of that and said, instead of saying infected or infective, I'm sending a message exposed. Why? Yeah, why might they not get infected? If we send it to a given person, why might they not get infected? Yeah, they're recovered. They're already infected. I mean, they're not necessarily ready for it. Okay, great. Okay, now we can run this model, but we won't see with clarity what's going on. What do we need to do to see with clarity what's going on? Well, we need to add a little bit of color to sort of distinguish things. We don't actually have to. It's not a matter of functionality. It's epiphenomenal. It's not going to affect the governing processes in the model, but it's useful. And so we're going to add in a variable color. Here we go, color. And its type is going to be color as set by the Imperium of the US. Color or naming convention or spelling conventions. Color. And its initial value is going to be blank. No, it's going to be black. And when someone is susceptible, the color will be, I'm going to change the color of the state to be lime, and I'm going to say color equals lime. Oh, color equals lime. When I'm setting this variable to the appropriate color. For the infective state, here we're going to have color equals red. And for the recovered state, here we're going to have color equals gray. Okay? Gray. It helps you see how it's spelled too. Okay. Ladies and gentlemen, here, color is something of type color. We give it a default value, but as soon as we come into any of these states, we set its color accordingly. What's the final thing we have to do to complete this pattern? We just added half the pattern, or actually 2/3 of the pattern. We added the variable, type color, and then we set the variable these various places. There's a final piece of this pattern for it to be meaningful in terms of changing the agent's color. What is that? Yeah, we have to set the oval color there. So let's go up to the oval. Let's go to the appearance thing. You may have to expand it. Set it to be dictated by color. There we go, ladies and gentlemen. There we go. Okay, ladies and gentlemen. Now we should be able to run this model, and we should be able to see some outcomes. Before doing that, I'd like you to go to main. We're going to add in one final pattern that should remind you of things that we covered some weeks ago now. We are going to go put in place a mechanism that will count the number of people that are infected in this model. How do we do that? How do we count the number of people that are infected? Yeah, population and statistics, ladies and gentlemen. Go to statistics. We're going to have a statistic called count infective. This is going to be a count, ladies and gentlemen. And you notice for the condition, it tells us each successive person is called item. So we're going to ask each person in the population, in other words, each successive item means each person in the population will be called item. We'll ask, are they in the state person dot infective? Why person dot? Because it's infectivity with respect to persons here. Okay, there we go. Okay, so what did I do there? I went and put in place in main a statistic in population. I scrolled down, went to statistics, named it count infective. It's a count. The condition will be item.instate person.infective. Build early, build often. Okay. The final thing we're going to put in before we run this model is we are going to place in here in the analysis, from the analysis tab, we're going to place in a time plot, ladies and gentlemen, a time plot. And this time plot is going to characterize the number of people that are infected over time. Okay, so this is going to be called prevalence time plot. Okay, time plot, and I'm going to put the title. It will be prevalence of infection. In other words, the number of people that are currently infected, and its value will be given by population dot count infective. Okay, great. Population dot count infective. What is this count infective? Who created that? Yeah, it's the statistics. It was the statistic we just defined in population, ladies and gentlemen. We created it. That was the statistic we created not 5 minutes ago here in population, and that's what's going to be plotted in this data set. Okay, the data update is going to say it will update automatically. Happy, happy. Okay, finally, I would like you to check two things. First of all, because some people have encountered problems with it, go to connections and make sure in communication, connections for person, make sure you're looking at the connections for person. Make sure that it says forward messages to this state chart, okay? So in person, you may have to scroll up. You could see connections. I'd like you to make sure that you are forwarding messages to the state chart. This is the same place before we check draw line connecting agents. If this is not checked, check it, because you will need the messages to be delivered to that state chart. Next, in simulation, ladies and gentlemen, I would like you to go and I would like you to to model time in simulation, and I would like you to set it so it stops at time 1,000. And we need to then configure this plot to draw between time 0 and 1,000. So for the plot, so in other words, simulation, I went to model time, and I set it to be time 1,000. In the simulation, also set randomness to be random seed. This is very important. So in the simulation, go down to the randomness area, set it to be random seed, so every time it's different. And then in the plot, in main, we will set it to display up to 1,000 latest samples, and we will set the time window to be 1,000 time units. How did I do that? I went to main, I clicked on the time plot, I said here in the data update area, display up to 1,000 latest samples, and in the scale area, I set a time window of 1,000 model time units. So if we run this model, what should we see? Does anyone want to predict? What will we see in terms of that graph? Do you think if I ran this again, would I see the exact same thing again? Why not? Because of the random seed. In fact, the network is different. The chance of who infects whom is different. You'll notice that there's variability. There's a certain regularity being captured. It seems to settle right around a mean of roughly 40 in terms of number of people infected. But the details are different. Details are different. And it's hard to pin down just how different they are, okay, from each other when you're watching them one by one. So, ladies and gentlemen, we're going to put in place a mechanism that will allow us to reason through about the behavior of this model, not just for one single run, but for many runs in succession, and summarize those results, okay? It'll allow us to capture the commonalities between these runs and recognize where they're different, where there's variability. Okay, so this is what I want you to do. I'd like you to go to the model as a whole and do new. By the way, does anyone need me to post this model to Moodle? Would that be useful? You want me to, anyone? Going once, going twice? Yeah, I see some heads nodding, not nods heading. Okay, okay, I'm going to pause for just a second. I will go over here to Moodle, and I will post that in case you would like to use that. Okay, so let me just engage in logging in behavior. Here we go, boom, and I need to edit the page, and then I will go drag in this model. The model will be posted in the model's built-in class area of Moodle. And I will tell you when it's there in just a moment. Okay. And then here we go. And then it's under models. And here we go. SAR stochastics. Okay. So I have just posted it and told it to force download. So you can go get it there. It's called SRS Stochastic for anyone who needs it. Happy, happy. Okay, so ladies and gentlemen, we've seen this model. We have seen that it's variable from run to run, not surprisingly, because it exhibits positive feedback in a way that amplifies differences, and it exhibits some basic stochastics. So those differences in stochastic early on will be amplified by some of these positive feedbacks. So, for example, if a given person with lots of connections is first infected versus few, it'll make a difference for the subsequent trajectory. So, ladies and gentlemen, I'd like you to go to the model as a whole and say new experiment, and we are going to add in an experiment that's of different sort than we've ever run before. It's going to be a parameter variation experiment, okay? And this is going to be called, we'll just call it parameter variation, okay? Or no, let's call it stochastic variation. First, we're not going to do it with any parameters. We'll get to that later. Stochastic variation, okay? So what did I do? I right-clicked here, I said new experiment, and then I said parameter variation, and I accepted it. Now this experiment is going to be different from everything we've run thus far. Thus far, when we've run the model in an experiment, in a scenario, it's run the model one time and shown us the results. And that's of interest. To run a single execution of the model. This experiment is going to allow us, within a single fell swoop, a single button push, it's going to allow us to run the model many times. Okay? So I'd like you to go to this parameter variation experiment. And I would like you to go to the model time and make sure that its stop time is also with 1,000. Okay? Just make sure of that. Secondly, and actually even more importantly than the model time, I'd like you to go to randomness, and critically, I'd like you to set this to use a random seed rather than a fixed seed. It's actually not particularly sensible at all that the default for this for our needs would be fixed seed, because we want it to exhibit variability from run to run to run. That's the whole point of our needs. Okay, so this would be a random seed within this parameter variation experiment. Next, we are going to go and we're going to actually see what this experiment looks like, and then we're going to add a bit of structure to take advantage of it. So I'm going to go run this, and you'll notice when I run it, I come to a sort of open screen here, and if I run it, it just runs at a single time. Okay, I'm just doing that with that button. But let's go check this out a little bit more, ladies and gentlemen. In the parameter section of this experiment, we can either say vary parameters in range or freeform. What we want is freeform, and we're going to tell it to make 100 runs. Okay. Far from just running a single run of the model, we're going to have it run 100 successive realizations of the model. Actually, I say successive. I don't mean that literally. Some of them will run in parallel. How could they run in parallel? With modern architectures, how could they run in parallel? Yeah, one on each core. And in fact, there's any logic versions where they'll run them in the cloud. But here we go, stochastic variation. Here we go, and you'll notice that there's many cores on this computer, and they're running them very quickly, if you see that. Down here in the middle, you can actually see, as it's running them, many executed in parallel. If I did it for more runs, say 1,000 runs, you could see it with greater clarity. Here, I'll do this, and in the bottom, it's showing the updates as it's running. Successive ones, 270 have been run, 382, 504. It's running this model hundreds and hundreds of times, now 1,000 times, with each run going from the start to the finish, ton 0 to ton 10,000. It's extra fast because it doesn't need to go through the animation of it as well. Okay? Okay, ladies and gentlemen, I would like you now, having seen that, we're going to put in place the mechanisms to record how those runs are different from each other, how they're variable, how they differ from each other in terms of their results. So I'm going to illustrate this in two phases. First, I'm going to put in place something we've created before that should be familiar to you from our presentation on networks a few weeks back. Here, we're going to, when we run this model, for each run, we're going to take the final number of people that are infected and put it into a histogram. And that histogram is going to summarize, it's not going to be a histogram over time, of the number of people infected. Rather, it's going to be a histogram summarizing the distribution of people across different runs at the final time, time 1,000. Time 1,000. Okay? So let's go do that. So what we're going to do is, and that same principle will then be held for a more complex construct called the 2D histogram. So I'm going to go to the stochastic variation experiment. Next, I'm going to go to the Java actions area. Okay? Okay, now the actions are started, ladies and gentlemen. And you'll notice that there's this broad set of things that we can fill in. So before each experiment run, do this. After each simulation run, do that, etc. And we're going to make use of this, okay? So, ladies and gentlemen, what I'd like you to do is to go to the palette, and we're going to drag in from the analysis palette into this experiment, to the stochastic variation experiment. We are going to drag in two things. The first thing we're going to drag in is a histogram, okay? And this is going to be a histogram called final prevalence histogram. It's going to indicate the final prevalence of the model in terms of count of people infected at the final time. Now, secondly, and critical for this histogram to have access to its data, we're going to drag in what's called a histogram data object, ladies and gentlemen. Histogram data object. And the histogram data object is going to be the thing that actually figures out how many instances lie in this range or that range or that range, because that's what a histogram provides us, a sense of, the frequency with which a value falls in this range or that range or this other range. So the histogram data here is going to be called final prevalence histogram data, okay? And we're going to divide it up into 20 intervals. And we're going to put in place, ladies and gentlemen, here a value. But the value that we're going to put into place will actually not be specified declaratively here. We won't just say add this. Rather, every time we run the underlying model, we will take the value out. We'll salvage the value before that model is destroyed, and we'll put it into this histogram. Okay? So in order to do that, we're going to go back to the stochastic variation experiment. By the way, everything I'm talking about now could be really helpful for problem set 4. So just be aware of what I'm doing here is very useful for your machinations, for calibration, for example, or parameter variation experiments. So before each experiment run here, I'd like to put into place, I'd like to clear the histogram. So I'm going to say final prevalence histogram data, final prevalence histogram data dot reset. Okay? Dot reset, ladies and gentlemen. Next. So in other words, before I run each experiment, I'm going to clear out whatever data is there. Next, I'm going to also in that area, after each simulation run, I am going to put into place, I'm going to grab some data from the model that's just been run. I'm going to grab the final prevalence, and I'm going to put it into this histogram data object. And then the underlying model from which I've rescued that prevalence is going to be destroyed because it's got to run another version of it, and another one, and another one. And so each time it runs, just before, just after it finishes, I'm going to grab the information I need from it to put into that histogram, put it in the histogram, and after that, I'm done with that model, that main that ran. And main can be destroyed, and another main can be created, and the model run again. So after the simulation run, here I'm going to say final prevalence histogram data dot add, because we're going to be adding this into the histogram. And what am I going to add? What do you think I'm going to add? What do I need to add into this histogram? Yeah, the final prevalence. So the prevalence at the final time. The model's just finished running, so it is at the final time. And so we're going to say, and you'll notice there's this little thing here. It says use root to be the top level agent. What this is saying is root is the name of main. So I'm going to say root dot, guess what I say? If root is main, what can I ask for to get the prevalence? Population, you got it. Population dot count infected. Count infected. Okay. So after the simulation run, I'm going to retrieve from the simulation, from main. The main happens to be called here root. From the population, which computes the statistic, I'm going to get the count of infected people, and I'm going to put them into this histogram data object here. Okay? So that's what I'm going to do after each simulation run. I'm going to salvage this information I need from main, and I am going to then add that information in to this final prevalence histogram data object. The final thing, which I haven't done yet, but it's a key connection, I'm going to make this histogram depend on what? Histogram data object. Yeah, so I have to say sort of final prevalence will be the title. And where it confusingly says histogram, it'll actually be final prevalence histogram data. There we go. So the histogram here is just the visual display of it. It needs to depend on this prevalence data object, which I just populated, this prevalence data object here, which I just populated in that place after the model runs. I get the information to put in there from the model that just ran and put into here. Notice that all of this, ladies and gentlemen, is an experiment. The experiment outlives main. The experiment here is running 1,000 times it's running main. And each time it runs main, it runs it to completion, grabs this information it needs, adds it into the histogram data object, which is then auto-magically updated, which then is shown within this histogram itself, which refers to the histogram data. So let's run this thing. Let's run this thing here, ladies. Oh, it's unhappy. Okay, build early, build often. A rookie mistake on my part. I forgot the semicolon, ladies and gentlemen. Okay, forgot the semicolon. Here we go. We're going to run it. There we go. And I'm running it. And there's our histogram. Our histogram is being filled in as it's making successive runs. And it looks reassuringly like a what distribution? Somewhat like a normal distribution. That's right. Now, this is showing the prevalence at the final time of the model. Let's suppose we wanted to see how this changes over time. We could extract several of these. We could have 10 of these for different samples of time, but we can do a lot better than that, ladies and gentlemen. And we're going to do so now. Okay? We're going to put into place a somewhat more complex construct, but we basically initialize in the same way, and we'll basically be adding things to it in the same way. It will just require a little bit more finesse. So, ladies and gentlemen, let's go down to main. Let's go down main. Okay, I would like to go here, ladies and gentlemen, and I would like to put into main a construct which not many of us have used. It's a construct, no, excuse me, I think you did use it in one assignment. It's a construct called the data set. And this is going to be the prevalence of infection data set. This data set will accumulate the prevalence of infection over time. Okay? This data set is going to accumulate the prevalence of infection on a periodic basis, which we'll then use and summarize in the experiment across multiple different realizations. So, pursuant to that prevalence of infection data set, I'm going to keep up to 1,000 latest samples. And critically, this is absolutely critical, for this data set, we want to uncheck this default use time as horizontal value. So, excuse me, I speak wrongly, excuse me. We actually keep it checked here because we are using time. And the vertical axis value here will be, anyone want to guess? Yeah, the count infected. So population dot count infected. Okay. Okay. And we'll keep up to 1,000 here. Okay. And here it's saying do not update automatically or update. I'm going to say update automatically every day. It will update from the count of infected. Okay. Now, if we were to run this model once, we were just to run, not the stochastic variation thing, but if we were to just run it once and run it till it's done, ladies and gentlemen, we could go look at that, and here's our data set. This is quite useful. We can actually right-click on this data set, say copy, and we can go here and, for example, go into Excel and then engage in pasting behavior. Okay, so there we go. There's our data set. But our interests here, we can also graph it out. Boom. But our interests here are a little bit different, ladies and gentlemen. Our interests here are using this to inform a summary across many runs of this model. So we will now, having put this here, this is now a resource for us to salvage. Okay? We are going to go over to the experiment, the stochastic variation experiment. And just like before, when we finished each run, we placed it in this histogram data object, which was then summarized in the histogram here. We are going to salvage the data in this entire sequence over time, how many people are affected for each point in time, and summarize it what's called a 2D histogram, and 2D histogram data. So let's go back to the palette, back to the analysis area of the palette. I'd like you to drag in two things. The first is something called histogram 2D. Histogram 2D functions just like histogram above, but it shows it on a two-dimensional basis. So, ladies and gentlemen, this is going to be prevalence histogram 2D. Okay? And we want it to show bins. You notice up the top it says we have a choice. I want it to show the bins, not the envelopes around the mean, but the bins. Next, we're going to drag in here a histogram 2D data object, okay? Histogram 2D data. So this is going to be prevalence histogram 2D data. Boom. Okay. Now, and this next part is critical. We are going to put in place in the x-axis range and y-axis range for this histogram 2D, we're going to put different information in place. For the x-axis range, we're going to put 1,000, and the range is going to be from 0 to 1,000. Number of intervals is 1,000. It's going to be, they're going to be in value from 0 to 1,000. It's going to be 1,000 bins, in other words, ranges in which we will count how many fell. And for the y-axis range, we're going to be putting 100 bins, and the range will be from 0 to 100. Okay? It doesn't always have to be that way. In fact, maybe be more general, I'll just show you. We could have 50 intervals on the vertical scale, or even 20, which would be cruder yet. Okay, so this is for the histogram 2D. What this is going to give us is a summary across many, many runs, where we're going to count the number of runs that fall within a given time bin, say time 10 to time 11. How many of the runs fell within, had 0 to 2 people infected, or 2 to 4 people infected, or 4 to 6 people infected, or 6 to 8? It's going to count for each of those bins, and it's going to show us a color accordingly. Okay? Next, we're going to set this 2D, histogram 2D, to depend, just like we said above, this histogram to depend on this histogram 2D object. You may remember that. Here, we're going to set this histogram 2D to depend on this histogram 2D data object. Okay? So this is going to be prevalence of infection, and the associated, what it calls histogram, is going to be prevalence histogram 2D data. Okay? That's just going to be this thing here. So I went to this histogram and told it to get its data from here. Okay. Ladies and gentlemen, the final thing we have to do is what? This is all nice to talk about this being the prevalence histogram, but what do we have to still do? What do we still have to do, just like we had to do it for this guy above? We have to add data to it. So to do this, go to the projects, go to stochastic variation, scroll down just where we went before, and just after each of these things that we put in already. Remember, we had to clear the histogram data object before. Guess what we'll have to do here? Clear the prevalence histogram 2D data. Prevalence histogram 2D data, histogram 2D data, we're going to have to reset it. Okay? After the simulation run, just as we did this, and we got the final count of infectives at the end, what do we have to do here? We added it to the histogram data above. What do we have to do here? Well, we have to add to this histogram 2D data the information across all times of how many people are infected. And I'll let you puzzle over where we're going to get that from. And whilst I, oops, this should be not relevant. Oh, come on. Oh, okay. Prevalence, come on. Prevalence histogram 2D data dot add. Where am I going to get the information about prevalence over time from? From Maine. Where can I find the data on prevalence over time? Yeah, the prevalence of infection data set. So just like up here, I took a single value out of Maine as calculated by the population, the statistic. Here we'll just do Maine dot prevalence of infection data set, and we'll add it into the 2D data. Okay? In short, the basic relationship here mirrors that above. Here we have a histogram. It depends on a histogram 2D data. We populate that histogram 2D data down here. We clear it up here, and we add values into it down here. And it's exactly the same thing. The histogram 2D data depends on this histogram 2D data. Histogram 2D histogram depends on the histogram 2D data. And each of them is, and that histogram 2D data is cleared here, and it is populated with values here. So let's run this thing. Let's run it, because time is short. Okay, so here we'll run it, and this is what we see, ladies and gentlemen. Can anyone summarize some regularities here? Let's go and pause this for just a second and make it a little bit bigger, because it on the big screen it seems a little bit small. So here we go. So we'll see that. What do we see within this lower plot? X is time, ladies and gentlemen. Y is the count of people infected. Color here is indicative of so the darkness of the color indicates the number of instances, the number of realizations where at a certain time, the actual range of number of infectives fell within a given area. So, for example, we would, if at time 800, the number of people was 40, we would increment that bin there. And then what we're seeing in color is the darkness indicates how big that count is. If it's white, none. If it's very light green, few. If it's dark green, many. So what are we seeing here? Could you summarize a few things? Yes, Paul. Okay, so they typically cluster right here on 40, and we could sharpen that a bit by saying, there's some outliers and so on, but probably 95% at least fall between, say, 20 on the lower side and 70 on the upper side, and probably even a tighter range than that. So very good. And probably the mean is somewhere around 40, 45. What else can we see in terms of regularities here? Okay. Okay. Yeah. So further out in time, there's more variation. So early on, there's actually a tremendous amount of commonality between the different runs. Almost all runs start low, rise, come down again, rise again, come down, and sort of oscillate there. But the further out we go in time, because remember, this is time here, the further out we go in time, the more and more regular it would be. But there's something else going on too, ladies and gentlemen. Something else that I'll highlight. Does anyone see it? Yeah, what's going on at the bottom there? You look further out, and it starts to get kind of dark. What is that telling us? The fact that there's this kind of small little fringe at the bottom. What is that saying? Yeah, there's some infections or there's some runs, and by judging by this, not a tiny number, a decent number, where actually the infection dies out entirely, so that by time 1,000, nobody's infected. In fact, you'll notice it's interesting. Or as time goes on, this becomes darker. Why might that be? Why might it be that as time goes on, it's more and more likely that nobody's infected at all? Yeah, the longer you go, the more kicks of the can you have, that just by chance, in one of these fluctuations we saw, those kind of rises up and down for a given run of the model, just you may remember, if we ran a single realization of this, we actually saw quite a lot of variability here. And the further out you go, the more and more likely it is, just by the luck of the draw, one of these will hit 0, essentially. And when you hit 0, the infection goes extinct, and it's not going to come back. It's not like system dynamics aggregate model where you could have 1/100th of a person infected, and it goes to and they'll still bounce back. Rather, this is a case where if you go to 0, it sticks at 0. It sticks at 0. It sticks in this new equilibrium, right? It's not a stable equilibrium, but it sticks there. So, ladies and gentlemen, here we see there's definitely a central tendency here, but there's also a bimodality. There's actually a mode at 0, which cannot be totally dismissed, and then it's very low probability until there's a much higher probability here as well. And in fact, you could see that lower mode up here in the upper left or the upper right, if you look for it. right? Here's the mode down here around 0. So most of them come here, but it's actually bimodal. This is not just chance it's not just if I run this again, this little blip here will disappear. It's actually substantial. Ladies and gentlemen, this is a model which has certain features that invoke certain regularities. There are stochastics. Those stochastics are amplified by the presence of reinforcing feedback. But you can get in locked-in states where once you have 0, the infection stays extinct. And despite the stochastics, there are certain common features there's an orderliness to this that cannot be totally dismissed. There's fluctuations early on. There's oscillations early, similar to what we might get out of an aggregate system dynamics model that dominate for the first 100 or so time units there. After that, there's a lot of variability from run to run, but there's a certain common range and a certain propensity over time to have the risk of the infection dying out. Stochastics, ladies and gentlemen, matter. We saw that with discrete event modeling, where stochastics in terms of the inflow and outflow could sometimes lead to an arbitrarily large waiting time or waiting list, for example. A system that in aggregate system dynamics we were characterized with equal inflows and outflows. Because of stochastics and the fact that the count of people waiting can never go negative, we can get this sort of asymmetry. Here, we see stochastics as important, but we can quantify the degree of those stochastics. We can bound their impact on the results, at least at a probabilistic level, characterize sort of the patterns that we see coming out of this. And we can see the effects of lock-in, and we could see the effects of nonlinearity, and we could see the effects of stock and flow dynamics in terms of some of these oscillations. So we're going to be exploring this more next time with two things. Number one, we're going to vary parameters and see how they affect this. And number two, we're going to be turning our lens to a very conceptually closely related process in terms of its implementation, in terms of how it runs the model many times, called calibration. And calibration is an important part of your final problem set. And so next, the material from this lecture, how we put in those sort of things within the experiment itself to gather information after each simulation run or to initialize it here. Those are going to be directly relevant for your final assignment. But we're going to see with calibration how we adjust parameters, not merely to examine their impact on the broad patterns, but to get the model to match as closely as possible the observed behavior. Okay, that's all for today. I did want to make two brief announcements. One announcement is that we will be holding a review session for this course, and the votes have spoken. That review session will be held the day before the final exam, following the conclusion of classes. So that is Thursday evening. Everyone could who indicated their availability could either make it or could do so if need be. Okay, and we'll hold that examination session in a room that has yet to be determined, but I'll be working with my secretary to set that up so that we have a clear place. I will hold it for a few hours. If anyone is simply not able to make it, rest assured that I will do my best to make sure that it is recorded and that it is placed online immediately following it. Naturally, anyone who went and wants to review something may also find those recordings of use. So that's announcement one. Final exam review session, I'll be sending out information about that. Number two, there was a question on the assignment. The final assignment, assignment 4, is for both 394 and 858. There was some confusion because I guess one of the labels said 858, but please rest assured that it is a 394 assignment as well. And as always, I'm happy to answer questions about these assignments, particularly during office hours following this class. Thanks very much, and we will see you on Thursday. Good luck with the end of semester work. Yeah.
So
Yeah.
question. I
Yeah.
was wondering, what will the final exam be like?
The final exam